In this video, we're going to go over unique cases of balancing redox reactions, such as disproportionation reactions, as well as reaction equations where there's going to be more than two main actors. Okay, so with disproportionation reactions, those are reactions that occur when a species or a chemical substance, so I'm just going to go with a species, is both the oxidizing agent as well as reducing agent. So you do need to know what a disproportionation reaction is and how to identify it, as well as how to balance them. So to balance these reactions, you got to write the substance that is being both oxidized and reduced twice. So in this video, I'm going to be using the half reaction method for balancing these redox reactions. Okay, so your key clue to tell you that a disproportionation reaction is happening is when one certain element shows up in your product side twice. Okay, so it's got to be a unique substance. It's not going to be something like hydrogen or oxygen. So for this example here, notice that we have manganese. It shows up once in the reactants, and then on the product side, it shows up twice. So that gives me a clue that disproportionation may be happening here. Okay, so what I'm going to do is I'm going to ignore hydrogen or hydrogen ions and water, and I'm just gonna pick out what looks similar. Okay, so keep in mind for each half reaction, I'm only selecting two things, one on the reactant side and one on the product side that looks similar. So for this reaction, I'm going to select this, which is a manganate ion, not to be confused with permanganate ion, and this manganese oxide. Okay, so let's write that out. Aqueous goes to manganese oxide. Okay, and then for my next reaction, actually, you know what? I'm gonna move this manganate ion just a little bit over. There we go. Okay, and then for the next reaction, again, I'm just picking what looks similar on the reactant side and product side. So I'm gonna pick the manganate ions and then this permanganate ion. So I'm making sure to line up my reaction arrows. Again, do not put an equal sign where you mean a reaction arrow. Okay, so let's use the half reaction method of balancing this out. So first things first, I'm going to make sure that everything that isn't oxygen and hydrogen is balanced. So for both of these reactions, for manganese, we have one going in, one coming out for both of these reactions. So manganese is already balanced. So now I'm going to move on to balancing out the oxygens using water. So on my reactant side for this first reaction here, I've got 4 oxygens, and then on the product side, I have 2. So I'm going to go to the side that has the least amount of oxygens, and I'm going to go plus 2 waters. Okay, so now I have 4 oxygens on both sides, and now I need to move on to the next reaction, just doing the same thing. So I've got 4 oxygens on the reactant side, and I've got 4 on the product side. So the oxygens are balanced. I do not need to add water to the second reaction. Now we're going to move on to balancing out the hydrogen. So again, I'm talking about this first reaction here. So I've got 2 times 2 hydrogens. So I've got 4 hydrogens on the product side and none on the reactant side. So I'm going to balance that out with hydrogen ions. Okay, so now that the hydrogens are balanced in the first one, I'm going to do the exact same thing for the second one, but notice how the second reaction doesn't have any hydrogens in it, so I don't need to add hydrogen ions anywhere. Okay, now we need to move on to balancing out charges. So with that, I'm going to find the total charge on the reactant side for the first reaction. So I've got -2 coming from the manganate ion, and then I've got 4 times 1 plus, so +4. So that's going to give me +2 on the reactant side for the overall charge, and then on the product side for the first reaction, both of them are neutral, so I have a total charge of 0. So I'm going to go to the more positive side, which in the first reaction is the reactant side, and I'm going to add 2 electrons there. So +2 minus 2, that equals 0. So now we have the same charge, the same overall charge on the reactant side as well as the product side. So now we're just going to do the same process all over again for the second reaction here. So I got a -2 charge on the reactant side, a -1 charge on the product side. So going to the more positive side, I'm going to add 1 electron, and now we have the same charge on the reactant and product side for the second reaction. Okay, so now at this point, we are looking to make sure that we're canceling out our electrons. So we're asking ourselves, okay, what is the lowest common multiple between 2 and 1? Well, that's going to be 2. So I'm going to multiply this second reaction by 2 and make sure that I actually remember to multiply every single thing in this reaction by 2. Okay, so now that we have the same amount of electrons, but one on the reactant side, one on the product side, those cancel out. Okay, if you have a case where you have 2 reactions where in both reactions you have the electrons only on the reactant side, you're doing something wrong. If you have 2 reactions where your electrons are both on the product side, you're doing something wrong. For redox reactions, one of your half reactions should have the electrons on the reactant side, the other one should have the electrons on the product side. Okay, so you have both reduction and oxidation reactions happening for a redox equation, redox net ionic equation. Okay, so now at this point here, I'm just going to check to make sure if there's anything else that cancels out here, but there is not. So I'm going to go ahead and move into my net redox reaction. So I got 1 manganate ion here, and we're adding these 2 here, so that's going to give us 3 manganate ions plus 4 hydrogen ions, and that's it for the reactants. Let's go to the products. So we've got manganese oxide. Actually, that should be manganese 4 oxide, I should be saying there. Solid plus 2 waters plus 2 permanganate ions, aqueous. There we go. So don't forget to write charges and states where applicable here. All right. So all of these practice questions are going to be very similar to the example that I just did. Figure out what your 2 half reactions are. Balance everything that isn't oxygen and hydrogen first, then balance oxygen using water, then balance hydrogen using H+ ions, and then balance the total charges using electrons. Then you're going to add up your reactions so that the electrons cancel out. So you're probably going to have to multiply one, if not both of your reactions by a certain amount to make sure that your electrons get to some lowest common multiple, and then you're going to add everything up. So moving on to equations where there are more than two main actors. So essentially here we're just asking, okay, what if there's more than two actors, which means like what if there's things that are other than oxygen and hydrogen in our redox reactions that are important? What do we do? How do we balance these reactions? So we're still going to split these into two half reactions, but never more than two half reactions. Okay, and then we're just going to balance like normal. Okay, so this is why I've been focusing on the half reaction method. It's just because it's a lot easier to balance redox reaction using the half reaction method compared to using oxidation numbers. So let's do an example together here. Okay, so once again, I'm ignoring hydrogen and water, and I'm just going to pick what looks similar on both sides of the equation here. So I'm going to start out with copper 1 cyanide. Okay, and then I'm going to pick what looks similar to that on the product side. So because we're dealing with equations where there's more than two important chemical species, this is why it's going to be a little bit different this time. Because if I looked on my product side, I noticed that this and this, so my copper 2+ ions and cyanide ions, they're both in here. So I need to pick those to use in one of my half reactions here. So copper, cyanide, aqueous, copper 2+ plus cyanide ions. Okay. And then for my other reaction, I'm going to pick this. So that's a chlorate ion, and then I'm going to look on my product side and say, okay, this is the only thing that kind of looks similar to it, so that's what I'll use. Okay, so now we're just going to go through our normal half reaction balancing steps. So step 1, I'm starting with the first reaction here, and I'm balancing everything that is not oxygen or hydrogen here. So copper, we have 1 going in, 1 coming out, balanced. For carbon, we have 2, because these brackets make this subscript apply to everything inside of the brackets. So we've got 2 carbons going in and only 1 carbon coming out. So then I need to put a 2 here. Okay, for nitrogen, I have 2 coming in because of that subscript 2. And because of this coefficient, now I have 2 nitrogens coming out. So those are all balanced. Okay, let's do the same for the next reaction. So I'm focusing on everything that isn't oxygen or hydrogen. So I've got 1 chlorine going in, but 2 coming out. So I need to put a 2 there. All right, now I'm going to focus on balancing oxygens using water. So with the first reaction, there's no oxygen in here, so I don't need to add water to it. For the next reaction, so I've got 2 times 3, so I've got 6 oxygens on the reactant side, so I need to have 6 on the product side. Okay, and actually I should use pink for that. Okay, so oxygens are balanced for both reactions. Now let's move on to the hydrogens. So with the first reaction, there's no hydrogens to balance, so we're good there. And then with the second reaction, I've got 6 times 2, so I've got 12 hydrogens on the product side. So I'm going to need 12 on the reactant side. So I better write it 12 right there. Okay, now we need to balance out the charges. So looking at my first reaction here, we've got a -1 coming from that copper 1 cyanide. And then on my product side, I've got +2, and then I have 2 times -1, so I've got -2, so that's equal to 0. So I'm going to go to the more positive of the two sides, and I'm going to add my electrons there. So I only need to add 1 electron here so that both sides have a -1 overall charge. Okay, for the second reaction, we're going to do the same thing. So we have 2 times -1, so that's -2, and then 12 times +1, so that's 12. So that gives us an overall charge of +10. And then on the product side, both chlorine and water are neutral, so that's an overall 0 charge. So I'm going to go to the more positive side and add 10 electrons, because if I go +10 minus 10, that's going to give me 0. Okay, so now both sides have the same charge for the second reaction. All right, so now I'm going to find the lowest common multiple between 10 and 1, which is going to be 10. So I'm going to multiply the first reaction by 10. I'm going to make sure I go through every single chemical species to do that. So 2 times 10, that's going to give me 20, and then 10 electrons here. So the electrons are going to cancel out, and I'm just checking to see if there's anything else that cancels out, but there is not. So I'm going to go ahead and write my net ionic redox reaction. So 10, there we go, aqueous plus 2ClO3, 1 minus aqueous, plus 12 H plus aqueous gives us 10 copper 2 plus aqueous plus 20 cyanide ions plus chlorine aqueous plus 6 waters. And there you have it. So the rest of these questions are going to be very similar. We're going to omit question 84, but the rest you should be able to do. Moving on to the next page, I just want to talk about the first question on this page that talks about photosynthesis. So you do need to know that photosynthesis is a redox reaction. You do have to be able to identify that reaction. It's pretty important. And you do need to be able to identify the oxidizing agents, reducing agents, and how many electrons are being gained or lost in everyday life reactions, such as photosynthesis. Okay, so for this question here, you're going to want to start it off by assigning your oxidation numbers to all species. So you're going through each element and figuring out, okay, what oxidation number or oxidation state each has. Okay, so if you want a review of oxidation states or oxidation numbers, I do cover that in a previous video there. Okay, just as a reminder, elements, they have an oxidation number or an oxidation state of 0. Okay, and remember for oxygen, when it's in compounds, usually oxygen has an oxidation state of -2 unless it's by itself as an element or in a peroxide, so such as hydrogen peroxide. The oxygen there will, each oxygen will only have an oxidation number of -1. Okay, but other than that, you should be able to do all the questions related to this reaction. I just wanted to explain this a little bit more.